Mechazilla catches a Starship. We've seen it work. But SpaceX has been quietly planning something different. Florida's new launch sites reveal a surprise in the environmental docks. Drone ship landings with deployable legs. Why abandon the tower method that's already succeeding? Because some missions demand flexibility. Can the proven Falcon 9 approach really scale up to Starship's massive size? Let's dive right in. LC-39A is set for NASA missions up to 44 launches. SLC-37 is designated for Air Force use, 76 launches approved. Both sites will have launch towers, yes, but here's the critical detail buried in the environmental assessments. Not every mission will return to those towers. Some flights are designated for drone ship recovery. This isn't a backup plan. This is intentional mission design. High-energy missions change everything. When you're launching payloads to geostationary orbit or sending cargo on direct trajectories to the moon, the booster burns longer and harder. It climbs higher, travels farther downrange, and consumes more propellant. By the time stage separation happens, there's a brutal calculation to make. Does the booster have enough fuel to flip around, fight its way back through the atmosphere, and return to the launch site? Often, the answer is no. And this is where drone ships become essential. Unlike a fixed tower sitting at Starbase or Cape Canaveral, a drone ship can position itself anywhere in the ocean. The booster doesn't have to turn back. It just keeps going and lands wherever the ship is waiting. This flexibility unlocks mission profiles that would otherwise be impossible with tower catches alone. The environmental documents outline potential landing zones that span 3 oceans. The Indian Ocean for certain orbital trajectories. The Southeastern Pacific for launches heading toward polar orbits. The Northeastern Pacific for missions requiring different inclinations. These aren't theoretical zones. They're mapped, assessed, and approved. Super Heavy gets recovery zones closer to home. The Gulf of Mexico and the Atlantic. But the ship? It could potentially land thousands of miles from its launch site. This is the hardware challenge SpaceX must solve. During flight, these legs stay retracted inside the vehicle's structure, protected from the heat and forces of ascent and re-entry. As the vehicle approaches the drone ship, they deploy, extending outward to provide a stable base. The ship touches down, legs absorb the impact, and the vehicle stands upright on the deck. Sounds simple? It's not. The aft section of Starship, where these legs would be mounted, is already packed with complexity. Engine bays, Raptor engines, propellant feed lines, avionics, hydraulic systems. Adding foldable legs means redesigning that entire section. It means strengthening the structure to handle landing loads. It means testing deployment mechanisms under extreme conditions. SpaceX removed legs from the Starship design years ago when they committed to Mechazilla. Bringing them back isn't just bolting on hardware. It's a fundamental engineering revision. For over a decade, Falcon 9 boosters have been landing on drone ships with remarkable consistency. Of course, I still love you. Just read the instructions. A shortfall of gravitas. These floating platforms have enabled SpaceX to recover boosters from missions that would otherwise be expendable. The success rate speaks for itself. Hundreds of successful landings with boosters flying again and again. However, Starship isn't Falcon 9. Not even close. A Falcon 9 booster weighs roughly 25 tons when it lands. A returning Starship stage, even with minimal propellant remaining, could weigh several hundred tons. The landing thrust from multiple Raptor engines? That approaches the full liftoff thrust of an entire Falcon 9 rocket. And with Raptor 3 engines on the horizon, that force will only increase. A Starship-class drone ship might need to be twice the size of current platforms. The deck must withstand not just the weight, but the concentrated force of landing, thrust channeled through those legs. The structure must remain stable in ocean swells. The deck must resist the heat from engine exhaust. And if SpaceX wants to recover multiple vehicles on a single platform, which would dramatically improve operational efficiency, you're looking at something approaching the scale of an aircraft carrier. Falcon 9 operates with 3 drone ships, and they're constantly in motion, sailing to recovery zones, returning to port, undergoing maintenance. Starship operations will be more demanding, more launch sites, higher flight rates, wider geographic spread. You can't run a global recovery network with 3 ships. You need redundancy, rotation, and regional coverage. This is where the financial and logistical challenges stack up. Building these platforms costs hundreds of millions of dollars. Modifying them for Starship recovery adds more. Crewing them, maintaining them, positioning them, it all requires sustained investment. And then there's the turnaround problem. You land the vehicle, you secure it, you transport it back, not to Starbase, which is thousands of miles away, but potentially to a new facility. Maybe California for Pacific operations, maybe Australia for Indian Ocean recoveries. These facilities don't exist yet. They'd need to be built, staffed, and integrated into SpaceX's operations. Each one represents regulatory hurdles, construction timelines, and local partnerships. SpaceX is considering all of this because the alternative is worse, being constrained by geography. If every Starship must return to its launch tower, you limit what missions you can fly. You turn down contracts. You compromise payload capacity. You slow down the development of lunar and Mars missions because you're locked into a single recovery method. The ship's re-entry performance remains inconsistent. Early 2025 saw multiple failures, burn-throughs, loss of control, vehicles breaking apart. Improvements came later in the year, but the heat shield is still not fully resolved. The ship must survive a long-duration mission, endure the violence of re-entry at orbital speeds, and still have precise control authority during the final descent. That's an enormous technical challenge. Super Heavy is further along. The successful Mechazilla catches in late 2024 and early 2025 proved the booster can be controlled with incredible precision. But SpaceX is still refining the approach, testing active flip maneuvers, adjusting landing angles, experimenting with reduced engine counts. Some recent flights look less polished because they were pushing boundaries. That's intentional. SpaceX needs margin, not just success. Every future mission to the moon will require legs. There's no Mechazilla tower on the lunar surface. Mars missions? Same thing. Early Starship landings on extraterrestrial bodies will rely entirely on deployable legs. Testing them on Earth, validating the design through drone ship recoveries, gives SpaceX flight-proven hardware before they ever attempt a lunar touchdown. Elon Musk referenced this back in 2023, discussing Falcon Heavy landings and stating, "And that's how we will land on Mars." The implication was clear. Legs aren't a fallback. They're a necessity for planetary exploration. If SpaceX ever launches from New York and lands in Tokyo, there won't be a Mechazilla tower waiting in Tokyo Bay. There will be a landing pad, and that pad will need to accommodate a vehicle with legs. Drone ship testing becomes the proving ground for this entire category of operations. So yes, this landing method is worth pursuing, but success depends on execution. SpaceX must formally introduce a leg-equipped Starship variant. They must build and deploy the drone ship fleet. They must achieve consistent re-entry performance. They must refine landing precision to the point where a moving ocean platform becomes a viable target. That's when SpaceX expects to hit several major milestones, potentially including the first Starship drone ship landing attempts. The V3 design upgrades currently in development are focused heavily on re-entry, survival, and landing control. Exactly what's needed for this approach to work. This is the company that said vertical landing was impossible, then landed boosters hundreds of times. They said catching rockets out of the air couldn't work. Then Mechazilla proved everyone wrong. Now they're saying Starship can land 2 different ways depending on what the mission demands. And honestly, that's exactly the kind of operational flexibility that turns an experimental rocket into a true transportation system. The critics will point to the challenges, the cost of building massive drone ships, the complexity of adding deployable legs, the weeks-long transport times from distant oceans. And they're right, these are real obstacles. But SpaceX has never been stopped by obstacles. They've been defined by how they solve them. This is SpaceX building redundancy into the architecture. This is SpaceX preparing for lunar landings, Mars missions, and global point-to-point travel. This is what it looks like when a company stops thinking about rockets and starts building infrastructure for a spacefaring civilization. If you found this valuable, hit that like button and share this video with anyone who follows SpaceX. And if you haven't subscribed to Space Update 24 hours yet, now's the time. We're covering every major development as SpaceX pushes toward full Starship operations. Thanks for watching. Keep looking up. SpaceX just caught a 233-foot booster using mechanical arms on a launch tower. The booster weighs over 200 tons and carries 33 Raptor engines. Each engine costs around $1 million. But here's what most people missed. SpaceX isn't just catching the booster anymore. They're building a tower system that catches both the booster and the upper stage. Why does that matter? Because every Starship stack costs $120 million in hardware. Without this tower solution, that entire rocket gets thrown away after one flight. Let's dive right in. To understand why this tower is such a breakthrough, we need to look at what rocket launches used to cost. For decades, the aerospace industry accepted one brutal fact. You build a rocket, you fly it once, and then you watch millions of dollars sink into the ocean or burn up in the atmosphere. Take the Saturn V. This was the rocket that sent humans to the moon. Standing 110 meters tall, it remains the most powerful rocket ever flown. Every Saturn V launch cost between $1.2 and $1.5 billion in today's money. The first stage alone used 5 F1 engines. Each engine weighed 8.4 tons and produced 690 tons of thrust. After launch, all 5 fell into the Atlantic Ocean. Never recovered, never reused, just gone. And this wasn't seen as wasteful at the time. This was just how rockets worked. But here's the question nobody was asking back then. What if you didn't have to throw away the most expensive part of the rocket every single time? SpaceX started answering that question with Falcon 9. In 2015, they landed their first booster. People thought it was a one-time stunt. Today, Falcon 9 boosters have flown up to 19 times. Landing on drone ships in the middle of the ocean became routine. The industry changed overnight. But even with Falcon 9's success, there was still a problem. The drone ship method works, but it has limitations. You need recovery vessels. You need ocean operations. You need time to transport the booster back to land. And you're still only recovering one stage. Starship operates on a completely different scale. The Super Heavy booster stands 71 meters tall and uses 33 Raptor engines. At liftoff, those engines generate 7,600 metric tons of thrust. That's more than twice what Saturn V produced. Each Raptor is a full-flow stage combustion engine, one of the most complex rocket engines ever built. Now think about this. If SpaceX threw away 33 Raptors after every flight, how sustainable would that be? This is where the Mechazilla tower changes everything. Instead of landing on legs or aiming for a drone ship, Super Heavy comes straight back to the launch site. After stage separation at around 65 to 70 kilometers altitude, the booster performs a boost back burn, re-enters the atmosphere,